principal component analysis. But we pretty much covered, we covered a big part of what we could actually use in a real situation. There is an assignment, it is ongoing, we will discuss it if you want to. But we will charge ahead now with the Monte Carlo simulation. One thing we must understand about Monte Carlo simulation is that Monte Carlo does not introduce any new rules in terms of asset dynamics. So Monte Carlo in itself is nothing but a clever way to implement the asset dynamics rules that we have already seen behind the parametric value at risk. Okay, what does a Monte Carlo do? Where does the name Monte Carlo come from at the beginning? The name Monte Carlo comes from the Manhattan Project. In the 40s, when they tried to build a nuclear bomb, essentially they invented scientific computing back then for this purpose. And they wanted to simulate, the way the bomb would explode. They would simulate this by running, in those computers of the 1940s, many iterations of random events, because radioactivity is par excellence a random event in nature. So they're simulating a nuclear reaction. And the name Monte Carlo was the military code they were using for these programs. And after that, the name stuck. So, what does a Monte Carlo simulation do? It generates future states of the world with the aid of random numbers. That's a very general definition of what the Monte Carlo does. Generally, in finance, a single simulation, it's called a path, which is a simulated course of events. And since Monte Carlo is a discrete method, we don't simulate every single instance of the future, we just sample. We may sample every day, every future day, every week, every quarter, every month. So each path is made up of a set of nodes. So a single simulation of the weekly closings of one stock is a single path which has 52 weekly future nodes. Now, if we have, obviously, we may be interested to simulate more than one things. We may be interested to simulate several stocks, or stocks and bonds, or stocks and interest rates. Then, at each node, what we have is not a future state of one thing, it's a vector of future states of many things. Generally, to arrive at the final distribution, we need many thousands of simulations. This ties in with what we talked about in the first lecture. You remember about the errors in a sample distribution, sigma in the sample distribution mean? And basically we said back then that the error on the sigma, the error on the mean, error on the mean was pretty much was proportionate. Let's say was proportionate to sigma over square root of n, and the error on sigma, I think, was proportional to sigma squared over to n. So I don't remember it. But the idea is, the more of n's I have, the more of an accuracy in a Monte Carlo environment I can get. And remember, n is not necessarily the number of simulations. And why am I saying this? Suppose I want to simulate a very simple derivative, a plain vanilla call option. Okay? Suppose I simulate it with 10,000 simulations. Okay. But this call option takes the price 0 for all prices below the strike price and takes the value of price minus strike for the prices above the strike price. If from my 10,000 simulations my strike price is such that only, say, 5% of simulated events I have a non-zero value for the option, then my real error on the value of the option is not as the square root of 10,000, it goes as the square root of 500, roughly speaking. And there are ways to basically direct your Monte Carlo simulation into areas of future developments that are relevant to what you're trying to find out. Because running a huge Monte Carlo simulation that's going to produce zeros in the overwhelming majority of cases is not a very good use of computer time. Generally now, when we have different scenarios, different paths, different nodes, the